When you think about the most pervasive, disruptive environmental stressor in your home right now, your mind probably jumps to the obvious things.
Right, like the stuff in the news.
Exactly. I mean, maybe you are thinking about the microplastics in your drinking water, or the air quality in your city, or maybe even just the sheer volume of noise from the street outside keeping you on edge.
Yeah, those are the usual suspects for sure.
But what if the most potent pollutant in your environment isn't actually something you eat or breathe? What if it is something you see?
It really completely reframes how we look at our living spaces, doesn't it? Because we are talking about light, specifically artificial light at night, which researchers in the literature refer to as a lamp.
And we are not just talking about it being slightly harder to fall asleep because your bedroom feels too bright. Looking through the sources we have for this deep dive, and I mean, it is a massive stack of literature. We've got NIH-backed research on circadian rhythms and huge epidemiological reviews.
Yeah, and some really dense molecular biology, too.
Right, so we are looking at something far more profound here.
The science is showing us that artificial light doesn't just annoy us or make us groggy in the morning. It is actively altering our biology at a cellular level. It acts almost like a hormone disruptor.
Okay, let's unpack this. Our mission for this deep dive is to decode exactly how artificial light hacks our master biological clock.
Which it absolutely does.
Right, and we want to unravel how it dismantles our metabolism, our mood, and even childhood development. And most importantly, by the end of this, we're going to arm you with a scientifically backed light prescription to help you reclaim your health.
That is the crucial part, yeah.
But to really understand how light breaks the system, we first need to understand how the body naturally tells time right.
Exactly. If you think about it, for 3 to 4 billion years, life on Earth evolved under incredibly predictable 24-hour cycle of solar days.
Bright sunlight during the day and near total darkness at night.
Right. And to survive, our biology had to internalize that rotation. We needed to anticipate the dawn, not just react to it when it happens.
So we need an internal clock.
Precisely. And the primary timekeeper in humans that does this is a tiny cluster of about 20,000 nerve cells. It's located deep in the hypothalamus, right at the base of the brain. It's called the Suprachiasmatic Nucleus, or the SCN.
So the SCN is essentially the conductor of a massive biological orchestra.
I like that analogy.
Yeah, you've got all these different organs, the liver, the heart, the kidneys, the digestive tract, and they all need to know when to play their parts. I mean, you don't want your liver trying to process a heavy meal when your body thinks it's 3 a.m.
No, definitely not. That's a metabolic disaster.
Right, so the SCN stands at the podium and keeps a tempo. But here's my question. The conductor is locked in a dark skull. How does the light physically get to that deep part of the brain to set the clock?
Well, the anatomy here is incredibly specific, and it's actually completely separate from what we normally consider vision.
Oh, really?
Yeah, when you think about seeing, you're thinking with the rods and cones in your retina, the cells that let you read a book or see colors or, recognize a friend's face.
Right, the normal visual stuff.
Exactly, but the SCN actually ignores those entirely. Instead, it relies on a dedicated non-visual pathway made up of specialized cells in the eye called intrinsically photosensitive retinal ganglion cells.
That is a mouthful.
It really is. We just call them ipRGCs for short.
Wait, hold on. If this is a completely separate pathway from rods and cones, does that mean someone who is completely blind in the traditional sense might still have a brain that is seeing the time of day?
Yes, exactly. You can have profound visual blindness, meaning you cannot see shapes or light or shadows at all. But as long as those specific ipRGC cells and their nerve pathway to the brain are intact, your body will still perfectly sync up to the sunrise and sunset.
Wow, that is wild.
It is. These cells aren't looking for images, they are solely looking for time. And they do this using a specific pigment called melanopsin.
Okay, melanopsin.
Yeah, and melanopsin is highly sensitive to a very narrow band of light, specifically the blue and green light wavelengths right between 460 and 480 nanometers.
Which just happens to be the exact kind of light the sun pumps out in the middle of a clear blue day.
Right. When those blue-green light photons hit the melanopsin in your eye, it triggers an electrical signal. That signal travels down a direct superhighway called the retinohypothalamic tract straight into the core of the SCN in the brain.
Now, in the sources, it gets a bit deep into the neurology here, talking about VIP and vasopressin. To keep us out of the medical textbook weeds, how does that signal actually get broadcast out to the body?
Think of it like a relay race. The light signal hits the core of the SCN, where neurons hold a protein called VIP. You can think of VIP as the first runner.
Okay, the first runner gets the baton.
Exactly. They grab the signal and hand the baton off to the outer shell of the SCN, which uses a different protein called vasopressin.
Got it.
Vasopressin is like the megaphone. It takes that baton and broadcasts the time signal out to the rest of the nervous system and the bloodstream. That entire relay race is how your peripheral clocks, like your liver, your heart, your muscles, know it's daytime and time to be active.
What really stands out to me is the sheer sensitivity of this ancient biological machine. I mean, it's incredibly precise.
What's fascinating here is the evolutionary context. This melanopsin pathway was perfectly calibrated for a specific environment. A world where daytime sunlight hits you with up to 100,000 lux of brightness.
That is a lot of light.
It's massive. But at night, even standing under a bright full moon, you're exposed to less than half a lux.
Oh, wow. So less than half the lux outside at night.
Right, our bodies evolved to expect that massive contrast. But modern lighting completely hijacks this pathway. We spend our days indoors in relatively dim 300 lux offices, and our nights staring at bright blue light, emitting screens, or sitting under LED ceiling lights.
So we've completely smoothed out the contrast.
Exactly.
Which brings us to what happens when this delicate non-visual system gets triggered at the absolute worst possible time, like when we are actively trying to sleep. Because my assumption, and probably most people's assumption, was always that when I close my eyes, it's dark.
Yeah, that makes logical sense.
Right, the eyelids are nature's blackout curtains. The system just shuts off.
Well, that is a very common and unfortunately very dangerous illusion. Light easily penetrates the eyelids. Even when your eyes are completely closed and you are fast asleep, those ipRGCs are still actively monitoring the environment for time signals.
Oh, man.
The sources detail a really illuminating study on healthy young adults. Researchers had them sleep in a room with just 100 lux of continuous light.
Just so we can picture, this 100 lux isn't like a stadium spotlight, right? That's just a moderate room light, like leaving a hallway light on with the bedroom door cracked, or maybe a bright bedside lamp.
Or even the glow from a large television left on in the room. And this study wasn't tracking them over months. This was just for one single night.
One night.
Just one night. The subjects woke up the next morning, reported that they slept fine, and were completely unaware of any issue. But their biological data told a very different story. Their brains perceived the sleep as highly fragmented.
Because of the light.
Right, because that 100 lux of light was constantly dripping through their eyelids and into the SCN. The brain was confused. It assumed the sun was coming up or that the body was in a state of daytime vulnerability.
So it actually shifts the nervous system.
All right, it shifted their autonomic nervous system away from the parasympathetic mode, which is your rest and digest healing state, and it locked it into the sympathetic fight or flight mode.
Here's where it gets really interesting, because the fallout from that isn't just waking up feeling a bit groggy or needing an extra cup of coffee. It creates a massive metabolic traffic jam.
It really does.
We were talking earlier about a car analogy. It's basically like leaving your car idling in the driveway all night, but you've got the parking brake pulled all the way up and you've got a brick resting on the gas pedal. You aren't actually going anywhere, you're just sitting there, but you are revving the engine to the red line and burning through the internal mechanics.
The tension in that analogy captures the biology perfectly, because when that sympathetic fight or flight nervous system is activated all night by the light, your body releases a steady drip of norepinephrine.
Which is a stress hormone, right?
Yes, and norepinephrine does something very specific in your metabolism. It actively blocks the glucose transporters in your skeletal muscles.
Meaning your muscles suddenly refuse to pull sugar out of your bloodstream. They just lock the doors.
Exactly. So glucose starts backing up in the blood. Your pancreas senses this rising blood sugar and essentially panics. It pumps out extra insulin to try and force that sugar into the muscle cells.
Oh no.
Yeah, the end result. After just one night of sleeping in moderate room light, these healthy young adults woke up with acute morning insulin resistance.
Just from the light. And when you compound that over years, the statistics are just staggering. Looking at the UK Biobank data in our sources, which tracks hundreds of thousands of people over long periods, it showed that for every 10 lux increase in a person's nightlight exposure, their risk of developing type 2 diabetes increases by 30%.
It's a huge jump.
30%. That means someone could be eating right, exercising, doing everything correctly, but because they have a street lamp shining through thin blinds, their metabolism is fighting a losing battle.
It also doubles the risk of high blood pressure, according to other epidemiological reviews in the stack. Normally, your blood pressure should experience a healthy dip at night while you sleep. The cardiovascular system needs that break.
Right, you need to rest.
But under artificial light, because that sympathetic nervous system is revving your engine, like you said, the nocturnal blood pressure fails to dip. Molecularly chronic light exposure causes a core clock gene called MPER2 to remain abnormally high.
And what does that gene do?
This essentially uncouples your liver and heart from your brain's master clock. It traps the body in a state of chronic low-grade inflammation.
Okay, so if just 100 lux of ambient light can dismantle a healthy adult's metabolism and cardiovascular system, we really have to talk about teenagers. Because you take a biological system that is already undergoing a massive hormonal earthquake, and you hand it a glowing blue light-emitting smartphone at midnight.
We have to look at the underlying biology first. When kids hit puberty, their natural hormones forcibly shift their circadian rhythm. they naturally develop what's called an evening chronotype.
Okay.
Their bodies physically delay the release of melatonin, the sleep hormone, by a couple of hours.
Which explains why teenagers always get that second wind at 10 p.m. They aren't just being rebellious when they say they aren't tired.
No, they genuinely aren't tired. Their clock has physically shifted. But here is the critical vulnerability that the sources highlight. Adolescents are significantly more sensitive to evening light than adults.
More sensitive.
Much more. The exact same amount of room light or screen light will suppress a teenager's melatonin far more severely than it will in adults. So their biology is already naturally pushing their sleep window later, and then the artificial light from screens weaponizes that tendency. It suppresses whatever melatonin they do have and pushes their internal clocks even further into the night.
And then society forces them to wake up at 6:30 a.m. to catch a bus for an 8:00 a.m. school start.
Which creates a permanent state of social jet lag. They are constantly sleep-deprived and severely misaligned with their circadian rhythm, but the damage goes far deeper than just fatigue.
Right, because the sources show that the light doesn't just go to the clock in the SCN. Those ipRGC light-sensing cells actually have direct neurological connections to the brain's limbic system, specifically the amygdala, which processes fear, emotion, and aggression, and the prefrontal cortex, which handles logic, reasoning, and impulse control.
This is one of the more alarming recent discoveries in neuroscience. Light at night physically alters the brain chemistry in these exact regions. It decreases a crucial protein called brain-derived neurotrophic factor, or BDNF, in the prefrontal cortex.
Let's visualize BDNF for a second. If the brain's a landscape, BDNF is like the construction crew paving a smooth asphalt superhighway. It helps neurons connect so signals travel fast.
Right.
So the prefrontal cortex, the logic center, the light stops the construction crew. The roads stay dirt and logic travels slowly.
That's a great way to picture it, but it gets worse. While it decreases BDNF in the logic center, the artificial light abnormally increases BDNF in the amygdala.
Oh, geez.
So it's actively paving superhighways in the fear and aggression center.
So you're starving the part of the brain that tells a teenager to calm down, and you are building a superhighway for the part of the brain that makes them lash out or panic. Well,
Yeah.
well, let me ask a broader question here. Are teenagers just naturally night owls and moody because of standard puberty biology? Or are we just blaming smartphones for a broader mental health crisis?
It's inextricably linked. The underlying biology primes them to stay up, absolutely. But the artificial light acts as the catalyst that turns a normal late bedtime into a structural psychiatric event.
Wow.
This combination severely disrupts the hypothalamic pituitary adrenal axis, the HPA axis. It spikes their cortisol, the stress hormone, at the wrong times. There are even MRI studies showing that this chronic circadian disruption from light leads to structural brain changes in teens over time.
Structural changes, like physical changes in the brain.
Yes, specifically reduce white matter integrity in the exact areas that modulate emotionality. It's linked to exacerbated anxiety, depression, aggression, and it even worsens PTSD symptoms.
It's literally rewiring the hardware of a developing brain. And if this light is powerful enough to alter brain chemistry and metabolism, it stands to reason it's affecting other hormonal systems too. This brings us to cellular growth and the melatonin hypothesis in the sources.
Melatonin is so often just sold in gummies as a mild sleep aid, but in the body it operates as what endocrinologists call the guardian of darkness.
The Guardian of Darkness. I love that title.
It is an incredibly powerful antioxidant. It flows through the body at night, clearing out reactive oxygen species, or free radicals that damage DNA. But crucially, melatonin also acts as a natural antagonist to estrogen. It puts a hard brake on estrogen production.
So when artificial light suppresses your melatonin at night, you lose that brake. Estrogen levels are allowed to rise unchecked. And over time, that prolonged estrogen exposure increases the risk of hormone-dependent cancers.
Yes, sadly it does.
The sources point to a massive meta-analysis showing a relative risk of 1.11 for breast cancer in populations with high nightlight exposure. And this was particularly strong for estrogen receptor-positive breast cancer.
And that loss of the melatonin brake affects children as well in a condition known as central precocious puberty, or CPP. In young children, high levels of melatonin at night naturally act as a brake on the onset of puberty by suppressing a hormone called GnRH.
So if a child is having heavy evening screen time or sleeping with too many lights on in the bedroom, they're essentially removing the brake prematurely.
The suppression of melatonin allows GnRH to pulse too early. Pediatricians are seeing cases of early puberty, such as breast development in girls before the age of 8, linked to this kind of disruption. Animal models exposed to chronic nightlight show this causes polycystic-like ovaries and severe systemic inflammation.
So the light is basically just...
The artificial light is functioning directly as an endocrine disruptor.
Okay, this next part from the research really threw me because it's so mechanical. It's about eye development. The actual physical elongation of the eyeball causing myopia or nearsightedness. The sources explain that bright daylight triggers the release of dopamine in the retina.
Yes.
And that dopamine specifically tells the sclera, the tough outer layer of the eyeball, to stop growing longer.
The eye relies on a massive contrast between day and night to know how to properly shape itself during childhood. A lack of bright daytime sunlight combined with sleeping with lights on at night stops that dopamine signal in the retina.
So it never gets the message.
The eyeball essentially never gets the chemical message to stop growing, so it elongates as it searches for focus, and that elongation is the mechanical cause of myopia.
There was a famous 1999 study in the journal Nature that looked at this exact mechanism. They found that kids who slept in rooms with regular room lights on had a 55% rate of myopia later in life, compared to just 10% for kids who slept in total darkness.
It was a very influential paper.
But wait, think about that study design for a second. If a kid is sleeping with a nightlight and gets nearsighted, couldn't that just be because their nearsighted parents are the ones leaving the lights on in the hallway so they don't trip when they go check on the baby at 2 a.m.?
That is a very sharp observation, and researchers actually asked that exact question a year later in 2000.
Well, they did.
Yeah, Griazza and Zadnik ran the numbers and found that parental genetics is indeed a major confounder in that specific 1999 study. Myopic parents do use more nightlights.
Okay, so the genetics factor is real.
It is. However, even after controlling for genetics in subsequent decades of research, the modern consensus in visual neuroscience validates the underlying mechanism. The dopamine sclera pathway is biologically sound.
Okay, so the light is still causing it.
The lack of bright daytime light combined with the circadian confusion of evening light absolutely accelerates the elongation of the eye in children.
All right, so what does this all mean for us today? We've talked about insulin resistance, anxiety, breast cancer, early puberty, and myopia. Knowing the sheer power of these non-visual light receptors, how do we actively reclaim our biology without tossing our phones in a river and reverting to the 1800s? The sources outline a very specific light prescription.
The overarching rule of the light prescription is that our bodies crave extreme contrast. We need incredibly bright days and pitch black nights.
Okay, so let's start with the daytime.
During the daytime, you need massive light exposure. We are talking about getting outdoors to get anywhere from 300 to 10,000 lux of natural light. You want light that is rich in those blue wavelengths around 5,000 to 6,500 Kelvin.
So basically just normal daylight.
Exactly. Doing this early in the day anchors your circadian rhythm, thoroughly suppresses daytime melatonin so it can build up later and protects eye development.
Okay, so blast yourself with sunlight during the day to set the clock. What about the evening?
The transition needs to start about 3 hours before you plan to sleep. You need to drop your ambient environment below 180 lux. Think dim table lamps, not overhead ceiling lights. And you want to shift the color temperature of your bulbs to warm amber tones around 2,000 to 3,000 Kelvin.
So what does this mean for the screens we all use? Can I just slap on one of those blue light filters or night shift modes on my phone at 11 p.m. and be fine? Or is the sheer brightness of the screen still going to trick my brain into thinking it's noon?
Brightness, the lux, matters just as much as the color. Even if your phone filters out the blue light and turns the screen orange, if you are holding a bright screen 6 inches from your face in a dark room, that raw intensity is still bombarding your ipRGCs with wakeful signals.
So still keeping you awake.
A blue light filter certainly helps take the edge off, but it is not a free pass to stare at a bright screen at midnight.
And when it's actually time to go to sleep.
Complete darkness. You want the room under 1 lux, you need blackout curtains, and importantly, you need to take some black electrical tape and cover the little glowing standby LEDs on your television, your air purifier, your phone chargers.
Because even those tiny lights penetrate the eyelids.
Yes, they seem tiny, but in a pitch black room, that pinpoint of blue or green light easily penetrates the eyelids.
What if I have to get up to use the bathroom? Or what if someone has an elderly parent who genuinely needs a nightlight to avoid tripping and falling?
For nighttime, safety color is everything. You must use amber or deep red lights somewhere between 1,000 and 1,600 Kelvin, and keep the source low to the ground so the light at eye level is below 51 lux.
Why red and amber?
Red and amber light wavelengths are so long that they barely trigger the melanopsin in those ipRGC cells. This means you can see perfectly well to walk safely down a hallway without resetting your biological clock or spiking your blood sugar.
It is incredible. We spent this entire deep dive unpacking the hidden power of this ipRGC to SCN pathway. It's almost like we have a second secret set of eyes that only look at time, not shapes.
That's a great way to put it.
And understanding this means that making incredibly simple, cheap adjustments to our environment. I mean, just changing a light bulb to amber taping over a charger LED or closing a curtain can protect everything from our insulin levels to our emotional stability.
If we connect all these dots, I think there is a broader implication to ponder here. If we now know definitively that artificial light operates on our biology with the potency of a hormone-altering drug dictating our cortisol, our insulin, and the structural wiring of our brains, should we start treating light pollution with the exact same regulatory urgency as chemical pollutants in our drinking water or smog in our air?
Wow.
It's something to think about the next time you reach to flip a switch in your house.
A hormone-altering drug hiding in plain sight right in the ceiling. Thank you for joining us for this deep dive. Stay curious, question your environment, and perhaps tonight do yourself a favor and embrace the dark.